All right, well, the students in here had a break. They went to the zoo yesterday, and they didn't invite me to come along and teach them algebra. So they have had a day to forget everything we talked about in the last lesson, but I'm going to refresh your memory. We began looking at columns and rows of numbers, something like, for instance, maybe this. And what do we call an arrangement of numbers in rows and columns? Kendall? A matrix. And if I wanted to name the matrix, Genesis, I would simply use... Well, yeah, it's consisted of rows and columns, but if I wanted to name this matrix, I would just use a capital letter. For instance, I might name this G for Genesis. Hey, this is the Genesis matrix. All right, looks very confusing and complicated. Anyway, now every number, every value in the matrix, Brandon, is referred to as an element. So not a term of the matrix, but an element of the matrix. And every element has an exact location or name based on where it is. Now these horizontal arrangements, class, are referred to as rows, and the vertical arrangements are called columns. So then this value here is in row 1, column 2. So what's the name of this particular 3, Audrey?
G. 1, 2.
G1, 2. You do the row location, then the column location. So where is the negative 2 located? What's the element number for the negative 2 right here? Genesis? G34. What number is in location G25, class?
1.
The positive 1 right here. What is in G31? This other 3. So one of the 3's is G12, the other is G31. Do you remember talking about this? We talked about the size of a matrix, and we said that the size of a matrix is basically the number of rows by the number of columns. So what is the size of this matrix, Maddie? I'm sorry? Good, it's a 3 by 5 matrix. That's going to be very important with what we're going to talk about a little bit later on today. But it's a 3 by 5 matrix. We said if we wanted to add matrices together, what had to be true of those matrices? They had to be the same size. So if matrix G is a 3 by 5 matrix, I can only add to it, let's go with an A matrix here, and I can only add to it another 3 by 5 matrix. So, just to be different, but anyway, just a little bit off. Not super weird or complicated, just picking on her now. But we could add these matrices together, and when we added them together, matrix G plus A would be another 3 by 5 matrix. What would we actually do to add them together, Kendall?
You corresponding elements.
There we go. I was about to call it corresponding elements. So my first element in the sum matrix, class, would be a 0, then
6, 1, 7,
3, 9, 2,
6. Very confusing right at the end, right? You feel like you understand what's going on, and all of a sudden, bam, out of left field, there's a 2. All right, so we get the idea of adding the matrices together. So we analyze these two individuals. What if I wanted to subtract a matrix? Well, in algebra class, we never subtract, we add the inverse. But for a matrix, we refer to the inverse for addition as the additive inverse. How would I make this an additive inverse, Audrey?
You put positive, and then you do negatives in front of all of them.
Oops, I can never stop. It's trying to go too fast. And that looks like a plus. All right, and we give her a very negative personality now. And there we go. Now we've added the additive inverse. So anytime you see subtraction, we would simply add the additive inverse. We also talked about multiplying a matrix, for instance, G, by a value. For instance, if we wanted to take 5 and multiply it by G, right? And we're expanding 5G coverage here to get what for our... I'm trying. All right. Thank you for the laugh. Okay, I appreciate that. You know, favorite student back there. Nice, good, hearty laugh, too. What would be 5G, Kendall?
Negative 5, 15, 25, 0, 30, 55, 10, negative 20, 45, 15, 35, 45, negative 10, 20.
There we go. Basically, just distribute the scalar all the way through. That's scalar multiplication. We worked on all of those things in our last lesson. Any questions on all the stuff we talked about last lesson? Because it was a couple days ago. Feel like we vaguely remember learning this at some point in our life? Okay, any questions at all on what we should already know before we get into today's lesson? So adding matrices, they just have to be the same size. And we just add corresponding elements together. It's very straightforward. Multiplying matrices. Next section, in your notes. Next section is multiplying matrices. This is where things get a little bit more involved, though hopefully by the time I'm done, you don't necessarily feel that it's necessarily hard. Under multiplying matrices, first things first, the number of columns in the first matrix must equal the number of rows in the second matrix. In order to multiply matrices, the number of columns in the first must equal the number of rows in the second. The number of columns in the first must equal the number of rows in the second. So you're not looking for matrices to be equal, you're looking for columns to equal rows, the number thereof, okay? When you multiply, well again, when you add, you have to have equal dimensions, right? 3 by 5, another 3 by 5. And what you get is another 3 by 5. For multiplication, columns must equal rows, and the resulting product matrix, the product dimensions, if you just get this down, the product dimensions will be the rows of the first by columns of the second. The product will be rows of the first by columns of the second. Don't worry, I'm going to make this make sense in a second. Hang in there, okay? I know right now it's like, whoa, okay? Product dimensions will be rows of the first by columns of the second. So let me show it here with this thing that's been frightening Maddie for a while. Okay, so we're going to try to make sense out of this poster for Maddie and for all of you. So if we have a 3 by 3 matrix, obviously we understand this tells me how many rows in the first, this is how many columns in the first. Rows in the second, columns in the second. These two have to match. The way I like to think of it is the inner numbers have to match, and the outer numbers are the dimensions of the product. So your product is going to be a 3 by 2, and you can multiply because these numbers match, okay? Technically, it is what I had you write down. So let's put this, for instance. If I had a 3 by 4 matrix times a 4 by 2 matrix, can I multiply? Yes, because they both have a 4. What is the product going to be? The product is going to be a 3 by 2. Does that make sense? So the inner dimensions have to match in order for you to multiply them. The outer dimensions give you the product. Now here's something important. What if I took the two matrices and I flip-flopped them? And I said, okay, let's multiply a 4 by 2 times a 3 by 4. Can I multiply these? No. The inner dimensions, the columns of first and rows of second, do not match. So write this in your notes. Multiplication of matrices is not commutative. Multiplication's commutative, sure, but multiplication of matrices isn't, unless they're both square matrices. Then you could reverse it, but you're going to get different answers when you reverse them. So matrices, you can't reverse the order of how you multiply them. So let's suppose I had a 1 by 5 matrix being multiplied by a 5 by 3 matrix. By the way, what do we call a 1 by 5 matrix? How many rows does it have? 1. How many columns? 5. So what's it called? A row matrix, because it has a single row. A 4 by 1 would be called a column matrix, because it only has one column, right? A 3 by 3 we call it a square matrix, right? Because it's got equal dimensions. Here, yes, I can multiply them because it's the 5s match. The columns and rows match. The product, when I multiply these classes, is going to be a 1 by 3. So again, if you try to think, let's do columns of first and rows of second. Okay, I can multiply rows of first and columns of second as the product. That's hard. But if you'll look at every matrix and write its dimensions, you can say inners match, good, outers match, that's my product. Make sense? So could I multiply a 3 by 2 and a 3 by 4? Can I multiply those? Why not? The inner numbers don't match, okay? Now can I multiply them? Yes, because the inner numbers match. What would the product dimensions be, Maddie? 3 by 4. All right, so do we all understand how to figure out whether or not you can even multiply matrices? All right, look at page 277 with me very quickly. Page 277 in your textbooks. Let's look at some actual matrices and see how would we do this. All right, so they give us two matrices here on page 277, and they ask, can you multiply A, B in that order, A times B? Well, to figure it out, we look at A and we say, what are the dimensions of A, Genesis? Up here at the top, what are the dimensions of this first matrix A? No, what are the dimensions of the matrix? Like rows, columns. It's a 2 by 4, right? What about B? What is B, Genesis? It's a 4 by 2. Class, can we multiply A times B in that order? Yes. What would our resulting matrix be? It'd be a 2 by 2 if we multiply. We're not going to do the multiplication yet, just making sure we understand. Could you multiply B times A? Well, what are the dimensions of B? 4 by 2. And the dimensions of A, can you multiply those? But what kind of matrix are you going to get? You're going to get a 4 by 4 matrix out of it. Does that make sense? Okay, so this, yes, those, now again, you're going to get different answers as well, by the way. AB and BA are not going to be equal matrices. I mean, one's a 2 by 2, the other's a 4 by 4. Of course, you're not going to get the same answers. Right? It happens you could multiply them in reverse. You just get different answers. Look at the next part for A and B. What's the dimensions of matrix A, Audrey?
3 by 4.
3 by 4. What about B?
3 by 4.
3 by 4. Can you multiply two 3 by 4 matrices by each other, class?
No.
No. Because the inner dimensions don't match. Do we see how to determine whether or not multiplication can occur? That's the first step, is figure out, can you do it? Before we talk about how to do it, can you do it? Turn to page 282. Turn to page 282. I'm not trying to beat a dead horse. I just want to make sure we're really good on this. I want you to do 1 through 9 the odd. Page 282. Do 1 through 9 the odd. You're going to, first of all, I would write down the dimensions and then determine, can you multiply yes or no? If you can, go and figure what the product dimensions will be as well. They don't tell you to do that, but because of where we're going, I want you to do that. Can you multiply 1 through 9 odd? If you can, what are the dimensions of the product going to be? Of course, number 9 is fun because there's 3 of them in a row. All right, number 1, the first matrix, Audrey, is a
1 by 3.
1 by 3, and the second matrix is a
1 by 2.
1 by 2. Can you multiply them?
No.
Nope. They're both row matrices, by the way. What about number 3? The first matrix, Brandon, is a,
4 by 3.
the second one is a
2 by 1.
2 by 1. Can you multiply them?
Yes.
And in fact, if you did, class, your answer is going to be a 1 by 1 matrix. That's a single element, right? So that'd be a pretty easy multiplication there. Taking a look at number 5. So answer would be a 1 by 1. Number 5, first matrix is Genesis. 3 by 3, second matrix. 4 by 1. Can you multiply them? Nope. Maddie, next one. First matrix. 2 by 2, second matrix. Can you multiply them? Yes. What are you going to get for your answer? A 2 by 1. How many have that for number 7? Kendall, on the next one. The first matrix is a
2 by 2.
2 by 2. The second matrix is a
2 by 1.
2 by 1. First of all, can we multiply those? Yes, and that would give us a
2 by 1.
2 by 1. We have to take the resulting 2 by 1, multiply by the next matrix, which is a
4 by 3.
4 by 3. Can I multiply that?
No.
No. So can I complete the multiplication problem? No. So there we go. How many had no, yes, no, yes, no? Nice pattern there. And we figured out the correct product dimensions. Do we feel like we understand how to figure out what we can or cannot multiply? Now for the process. Here we go. To actually multiply, distribute each row by each column. Write that down. To multiply, distribute each row by each column. Distribute each row by each column. Or maybe a better way to say it would be distribute each row to all columns. Might be another better way to say it. In fact, I think that's what we have here. Yeah. Multiply each row by all columns. Now I'm going to give you something that looks really mathy, but it might help this to make more sense in a moment. So when we multiply, the first thing we're going to get is we're going to get the sum of row 1, column 1. The first term in my matrix is going to be the sum of the row 1, column 1 products, or partial products, if you will. The next is going to be the sum of row 2, column 2. Down here is going to be the sum of row 2, column 1. And then here is going to be the sum of row 1, column 2, row 2, column 1, row 2, column 2. I just realized that's not written correctly. What am I doing here? Row 1, column 2. Okay, so row 1, column 1, the sum. Row 1, column 2, the sum. Row 2, column 1, the sum. Row 2, column 2, the sum. That's what we're going to be doing here in just a moment. Let me point out what we've got here. We've got our matrix A. It's a square matrix, 3 by 3. We've got row B is not a square matrix. It's 3 by 2. So our product dimensions here are going to be a 3 by 2. Do we see 3 rows, 2 columns? So we're going to take this first row and we're going to multiply it down this column, and that's all going to be the first term. So 3 times 7, 5 times 1, negative 1 times 4. Do we see we took these 3 numbers, multiplied it by those 3 numbers? The summation of all of that is going to be my first number. So that's a 21, a 5, and a negative 4, or positive 4, excuse me. Add those all together, you get 30. Then we took this row, then we took the same row and we drop it down the next column. Okay, so this row times this column, then the same row by the next column. 3 times 9 is 27. 5 times negative 8 is negative 40. And negative 1 times negative 5 is positive 5. We add all of those together, we get negative 8. That's that term. Then we take this row, drop it down here, do all those multiplications. The 2, the 0, the 4 get multiplied by these numbers, and the 2, 0, 4 get multiplied by these numbers. We take those partial products, add them. Partial products, add them. Then we take this row, multiply by the terms down here. So the negative 2, the 6, the negative 3 get multiplied by the 7, 1, and negative 4 now. The negative 2, 6, and negative 3 get multiplied by the 9, negative 8, and 5. We get all of our partial products, we add them. Get all your partial products and add them. That's the process we're going to do. So let's do one of these now as you go back to page 278. Actually, I think I'll have you watch this one. but you're going to help me with it. Page 278, we've got a matrix A is negative 1, 2, 4, 1, 2, negative 4, 3, 2. And then we've got matrix B is a 1, 0, 0, 3, negative 2, 4, 7, 5. First thing you do in any multiplication problem is figure out if you even can do it. If you can't do it, it's a lot quicker to say impossible than it is to spend a lot of time on it. So Maddie, the dimensions of my first matrix, 2 by 4. The dimensions of my second matrix, 4 by 2. Can I multiply, class? What's my answer going to be? Here's my suggestion. Make it big and make it 2 by 2. I'm actually going to set up a little grid. In fact, you can't see it because I erased it, but there was a grid work in here originally. Because I can't do it without the grid. I got to keep the grid to keep me focused. All right, what we're going to do is we're going to take the top row and we're going to drop it down the first column. So I'm going to start with negative 1 times 1 class, then 2 times 0, then 4 times negative 2, and then 1 times 7. That's that box. Now we're going to take the same row, drop it down the next column. Negative 1 times 0, 2 times 3, 4 times 4, 1 times 5. Do we see what we're doing? I'm done with the top row. The top row has now gone down the first and second columns. Now I'm going to go to the second row, and I'm going to take this and drop it down the first column, and then the second column. Does that make sense? So what numbers should I write? What are my partial products going to be here? Kendall?
2, 0, negative 6, 14.
All right, and then we're going to go down the next column, Maddie.
2, 12, 15.
Now we get to add the numbers together. And here's where I'm going to go smaller. And here's where a calculator can really come in handy. I don't think for most of the multiplications you're going to want it. Here's where you might want the calculator. You're going to add negative 1, 0, negative 8, and 7 all together, class, to get negative 2. That's my first element in my 2 by 2 matrix. Then I'm going to add the 0, the 6, the 16, and the 5. 27. Then I'm going to come down here. I'm going to add 2, 0, negative 6, and 14. And then I'm going to add 0, negative 12, positive 12, and 10. And there's my matrix. Now that you had a chance to see all that stuff I was talking about, that looks really complicated, do you feel like, okay, I get the idea? And do you see, by the way, why too, the number of columns has to match the number of rows, or you couldn't do the multiplication anyway. Does that make sense now? All right, questions on this before you have a chance to work one there at your seats with me. Yes, ma'am.
So you take the first one across and then you go down.
I go down. So I take these 4 numbers and I multiply by these 4 numbers. That's why they've got to be the same. These 4 multiply 1, 2, 3, 4. Then I take these 4 and multiply by these 4. 1, 2, 3, 4. These are called partial products. Then I take the next row with these 4 numbers and I multiply 1, 2, 3, 4, and those partial products go here. Then I take these same 4 numbers, multiply by these 4. 1, 2, 3, 4. Then I add to get my final product. All right, let's do page 283 now, number 11. Page 283, let's take a look at number 11. And we'll start with a pretty easy one, I think. Page 283, number 11. The first matrix, class, is a 2 by 2 square matrix. And I'm going to multiply it by another 2 by 2 square matrix, which means my product has to be a 2 by 2 square matrix. Here's my suggestion. Draw your 2 by 2 bigger and put a single cross in there to give you 2 by 2. That keeps your numbers from getting jumbled up with each other. We're going to start, class, by taking the first row and dropping it down all the columns, all both of them. So Genesis, let me have you do this one with me. We're going to start by multiplying this row by this column. I'm going to do 2 multiplications. I'm going to multiply here and here. Then I'm also going to go down the next row to go in this spot. So I'm going to get, all right, then I'm done with the first row. I've dropped the first row down all the columns there were. So now I switch to the second row. And I'm going to go down the first column and then the second column. So Genesis, what do I write here? -2, okay, and then I go down the next column.
4. -4.
Right, first times first, second times second. So -4, -6. Is it making a little bit more sense? Okay, good. We'll keep working at it. And so for my answer, I just have to add the partial products together to get the 4 terms of my 2 by 2 matrix, or 4 elements rather. What are my 4 elements, class?
3, 11, -2,
Feel like we're getting the hang of it? A lot of numbers, a lot of craziness going on, right? But once you see the pattern again, first by first, second by second, first by first, second by second. Next row, first by first, second by second, first by first, second by second. Let's take a look at number 13 now. Number 13. What is the first matrix dimensions, class? 2 by 3. Second matrix, 3 by 2. Can I multiply these? What am I going to get when I multiply? A 2 by 2 again. All right, so we got a 2, 3, -2, -1, 1, 0. Getting multiplied by 0, 1, 2, -2, 1, 3. Again, set up a little bit larger space for your matrix and give yourself a 2 by 2 grid. This time, Audrey, take your first column or first row, put it down each column. So give me all of my partial products that go in the first spot.
0, 6, -2.
All right, any questions on how she got 0, 6, and -2? All right, what about the next box, Audrey, the one next to it?
2, -6, -6.
Are we all good on the 2, -6, -6? You all keeping up? Brandon, go to the next row, drop it down the first column.
0, 2, 0.
All right, and then the next column.
-1, -2, 0.
All right, we getting it? All right, now comes the calculator, or a lot of sign number practice. We have to add the partial products to get the 4 terms in our 2 by 2 matrix. What are those 4 terms going to be? Maddie?
4,
Perfect. Getting it? Question. Not that you would get the same result. Could you multiply these if they were transposed? Yeah, because if you did, you'd have a 2 by 2 matching, you get a 3 by 3. So let's do that. Now let's take a 0, 1, 2, -2, 1, 3, and let's reverse the order because we can. You know, can't always do it, but we can here. And let's multiply a 3 by 2 times a 2 by 3. What are the dimensions of our matrix going to be now, class? Now we're getting a 3 by 3. We're getting a totally different size of matrix. So this time, maybe a little bit bigger still, and it's going to be a tic-tac-toe board, isn't it? For a 3 by 3. Okay? But we're not putting in X's and O's, we're putting in numbers. Maybe we play tic-tac-toe later. All right, so we start with our first row, and we multiply by all 3 columns. Here, here, and here. And let's go to Kendall. What do I write here? What 2 numbers?
0, and 2, 0, -1.
0 and -1. What about the next box, Kendall?
0, 1.
Good. 0 and 1. And then the next box?
-2. 0 and 1.
You're multiplying. 0
0
and 0. That was kind of annoying, wasn't it? Let's try the next one, Kendall. Let's go to this row now. We're going to do the same thing. Drop it down here, here, here. Tell me what to write.
4, -4.
First and seconds. First and seconds.
-2.
There we go. It's okay. That's why we're working on it. This is new. And by the way, we're going to spend a lot of time working on this when we come back after break as well, okay? So if you're like, at the end of the hour, I know we only got 10 minutes left, like, I don't know if I get this. It's okay. When we come back after spring break, we're going to review over what we learned 2 days ago, and then we're going to spend the rest of the time on this again to make sure we've got it. But let's keep working. Let's see if we can get it. Next one.
6, -2.
All right, and then the next one.
-4, 0.
There we go. Okay. Genesis. Let's take the bottom row, and let's go down, down, down.
Is that a 7 or a 1?
Sorry, it's a
Oh.
1.
2. -3. 3. 3. -2. 0.
There we go. Good. Now, because there's only 2 numbers in each of these boxes, the addition should be pretty easy. We just have to do 9 different ones. What do we get for our matrix, Maddie?
6, 4, -1, 6, 8.
All right. We feel like we're getting it now. All right. Let's do one more problem, and let's do the big guy. Number 15. Yes, yes. Copy it down. We're going to go out on spring break with a bang. After doing 15, you'll know I deserve spring break. Well, sort of. We deserve hell.
Oh.
We're grateful for anything other than that. let's be real, right? I mean, what do we really deserve? That's it. I mean, I actually had a really good message when I was in college, chapel. Somebody came in from Indiana and he was preaching a message. He's like, whatever you have in life, it's better than you deserve. Because you deserve hell. It's like, that's actually true. So from there on, there was like no complaining rule. You can ask Miss Danielle, Mr. McDonald's wife. She was there at college for that semester when he was preaching. And it's like from there on out, like you start to joke about or to complain about the food in the dining hall, which actually was pretty good anyway. It's like, well, it's better than I deserve. Start complaining about the roommates, but they're better than I deserve because like the devil and his demons are supposed to be my roommates in hell. So, you know, I mean, everything's better than we deserve. It's perspective, right? Perspective. Anyway, number 15. You saw that. All right. I won't say I deserve accolades, though, for that catch. I need to find the audio of that sermon. It was good. It was good. All right. Just made it really no fun to complain anymore. Let's be honest. Like half of our fun in life is complaining, right? Like husbands complain about their wives, wives complain about husbands, parents complain about the kids, kids complain about the parents. It's like, it's what we do for fun. Like that's even our jokes. Half our jokes are complaining, right? And then you go throw in something like that, and better than you deserve, and it sucks the fun out of life. All right, but it's good perspective anyway. It teaches us to be thankful, like we talked about in chapel today. All right, first matrix class, 3 by 3. Next matrix, 3 by 3. So our product is going to be 3 by 3. Let's make a big tic-tac-toe board. Okay, you start by taking the first row, and you're going to drop it down all the columns, one at a time. So we're going to start with just the first column. Brandon, what are my 3 partial products?
0, -3, -4.
0, -3, -4. Keep going, Brandon. The next 3 partial products in the next box.
2, -6, 0.
2, -6, 0. Audrey, take the next box as we go down the final column.
1, 3, -6.
All right. Now that we're done with the first row, we've dropped the first row down. The first column, second column, third column. There's nothing left for the first row. So class, we go to the second row. All right. What goes in this first box for my second row, Genesis? 0, 0, 2. Next box, Genesis. 4, 0, 0. And the last box, Kendall. Or the last box on this row, I'm sorry.
2, 1, no, 2, 0, 3.
There we go, 2, 0, 3. All right, we're done with row 2, so class, we now go to row 3. And we go down the first column. So Kendall will stay with you.
8, 0, -3.
Careful, we're starting it right here.
Oh, okay. So 0, -5, -2.
Good. All right, now we're going down second column with this bottom row. And what do I get, Maddie?
8, -2, 0.
Good, 8, -t, and 0. And for my last one here, let's go back to Audrey.
4, 5, -3.
All right, now then, it's time to put all the partial products together to get our final product matrix. Kendall, the moment is yours.
Okay, so -7, -4, -2.
This is a lot of negative in this matrix.
2, 4, 5.
Oh, that's much better.
-7, -2, and
Back to your old ways, I see.
-6.
6. There we go. Do we feel like we got it? Again, on the surface, when I first teach, it's really complicated until you start doing it and getting the hang of it. And then I feel like it should start to be settling in. How many feel like, I don't know if I'll remember this after break, but I think I got it now. Okay. Well, if you've got it now, then that means after break, if we do the same kinds of things again, it should be able to click again even after break. So that means I don't have to give you any homework over spring break. So no homework. And here in a few minutes when the bell rings, you will be on spring break.
Yeah, we're swimming home.
Swimming home. We had a tsunami. So anyway, pouring down rain and hail and things like that. Somebody said Michael and Abby wanted to go on vacation a day early, and God's like, not on my watch. So anyway, hopefully things went well for you so far getting out of town and wherever you were going a day early and missing my math class. I'm not bitter though, not bitter. Not bitter at all. Anyway, see you all in a week and a half and enjoy some rest.